Hello. Today I'm going to continue talking about the data link layer, in particular one half of it. The data link layer is broken into two parts: the media access control and the logical link control. We're going to begin with the MAC. Now, think of it this way. We have a local area network of computers that share some media. A typical example would be a group that is connected through a satellite. Another example would be a group of office computers which all use the same bus. To get a bus, remember, is just a cable that everybody connects on. The idea is that it's a shared media. We have to figure out how we're going to share it reasonably. And usually it's a media that everybody can hear. So it's not that secure, but we don't worry about it too much. Our plan is that every computer get a reasonable amount of time to send its messages. And on the other hand, the LAN doesn't stay, we get the most out of the LAN. We don't have it idle all the time. Now also, what we haven't mentioned is LANs have limits to how many computers they can have and the distance they can have. The reason for that is so that we can control the collisions between messages that when two nodes try to send at once. So there are three types of MAC algorithms. Channel partitioning, which basically means we break up the media into chunks and we give each of the machines and the nodes and the LAN a certain chunk to use. Random access with rules when two nodes try to send at the same time. And this is Ethernet, among other things. And then taking turns, which sounds reasonable but has its own problems. Channel partitioning comes in two flavors. Time division multiple access means we divide the bus, the satellite time, whatever, into fixed length time slots. Time slot starts at a certain point, ends at a certain point. They're all the same size. Each node is assigned one of these time slots in each cycle of them. If a node does not want to send when its time slot is available, nobody can send. Now that's the downside of this. The system becomes idle if a person who owns the time slot doesn't want to send. Excuse me. So, pardon me, I got that wrong. Yes, I got it right. I was reading something there, and it looked like I had it wrong all of a sudden. No one can jump in if the owner doesn't want to use it. Frequency division multiple access just says the bandwidth is divided. Each node gets a particular frequency to carry its message. If a node is idle, its frequency is not used. We're still wasting bandwidth. So channel partitioning can lead to problems. It would be especially bad if you had a lot of computers on the LAN and most of them weren't active all the time. Our random access protocols, this has a rich history. The state of Hawaii is hard to wire. You have a lot of islands, and the ocean between them is deep. So laying wires seemed to be a poor way to set up a local area network in Hawaii. So instead, the government gave research money to develop satellite systems. And the satellite systems became the bed for doing research on different ways of doing MAC. They were doing it on a satellite, but it could apply to a land based on wires also. It must have been interesting work to get assigned to work in Hawaii. The project was called the Aloha Net. Now, there were the first concept was when a node wants to transmit, it transmits. No turn concept. If two or more nodes send at the same time, the messages collide, and all the nodes hear the collision. There's a gobbledygook on the line. Well, that requires that we, first of all, have to make sure that the messages are long enough so that if our computers at two different ends of the network started sending at the same time, everybody would hear a collision, which means when one of the messages got to the other side has to still be sending for them to hear a clash between the two. So messages had to be padded if they weren't long enough. Then we need a protocol, what to do if they collide. This is what I was just saying. It takes physical time for a message to go along a bus or up to a satellite and back. It takes time. So everybody has to, the messages have to be long enough so that there's always a collision. Now, here were some algorithms that were used. Slotted Aloha. All the slots are the same length. We pad messages if necessary. Each node can only begin transmitting at the start of a slot. So that immediately means that if we make it long enough to get all the way across, that if the two of them, two on opposite ends, send at the same time, there will be a collision at both ends. The media is divided into slots by time, as I said. If two or more nodes collide, everybody hears this. So what do? They stop transmitting. They realize that they have to retransmit. And with some kind of probability, they choose among the next few slots to send. So we parameterize that by having a probability, and with probability P, a node resends in the next time slot, let's say, and with probability 1 minus P, it resends in the 2 time slots from that. The hope is that the two of them will not clash a second time. So I have it here. That same thing I just said. It's not very good. 37% of the bandwidth is used. So we should be able to do better than that. Pure Aloha says they can transmit anytime they want, but the messages are fixed length. And if a collision, they use probabilities as in the last algorithm. That took it down further, 18%. Now we're getting into the better methods. Carrier sense multiple access. MA is that everybody can access the same bus or satellite. carrier sense means that everybody hears everything that's out on the bus. Eventually, we all hear it. Now, what we do is listen to the channel. If the channel is idle, we can transmit. If not, we use a probability of some sort to decide how long to wait to send. We make the transmission long enough, there's two nodes at opposite ends of the channel begin sending at the same time. Every node still hears a collision. Now, we can go a little further than that and now add /CD for collision detection. This is Ethernet. I should say it's not strictly Ethernet. It is, for all purposes, Ethernet, but the heading is slightly different between the definition of CSMA/CD and Ethernet. I guess they just couldn't agree. If there is a collision, the sender randomly chooses a number from 0 to 1. 0 or 1, pardon me. The retransmission time is either 0-bit times later or 512-bit times. So if I choose 0, it's 0-bit times later. If I choose 1, it's 512-bit times. Now, if there's a second collision, now I choose a number from the numbers 0, 1, 2, and 3. And I wait 512 times that number. So now I wait 0-bit times, 512-bit times, 1024-bit times, 1536-bit times, or I guess that's it, pardon me. So I'm spreading them out. If there's a second collision, we do it again. We go up to 7 and wait that number of times 512. We keep doing this until we're choosing among 32 numbers, I believe it is. Now that method is called exponential backoff. So the first time we choose between two possibilities, the second 4, the next 8, the next 16, the next 32. It may go higher than that. I can't remember exactly. But the point is we go up exponentially 2 times each time we get a collision. It's more efficient than Aloha, and it's cheap and decentralized. I'm going to put up here 2 to some n, because I think it could vary. Now, that is the one that the world uses. Ethernet is everywhere. Algorithms, the other algorithms we'll talk about are the taking turns algorithms. This requires that there's some way to determine whose turn it is. Now, in the analogy to the fact that we're using a bus, we call the way you get on the bus as a token. I think you can call that cute or stupid, whichever you feel like. That a token is just a certain bit string of ones and zeros. It could be, for example, 8 ones in a row, or it could be 10, 10, 10, 10, 10, 10. It is a bit string that cannot be used in any messages. This bit goes around the network. Someone has to create it and start it by moving it to its right neighbor as if the nodes are arranged in a circle of users. They don't have to physically be in a circle. But if I'm a node on this LAN, I know who my next neighbor is on the right, and I have a neighbor on the left, the immediate neighbor on the left. It's as if we were in a circle. Again, you can have different configurations, but virtually you think of it as a circle. So I send out, if I get the token, I can hold on to it for a certain amount of time, and I can transmit a message. When that time's up, I have to send the token on, and I can't transmit a message anymore until I get the token again. So the token goes around the circle. Now, there's a problem. What happens if the token gets destroyed or lost? By lost, that would mean a bit gets a bit flips, and it's no longer recognizable as the token. Well, what do we do? Well, one thing would be to have somebody who's in authority, one of the computers, and say, you get to, if you don't get a token within a certain amount of time, you get to create one. But that's not the real way people should do it. The method usually is everybody's listening, and they set some kind of a timer. When they send the token out, they set a timer. If they haven't received the token back within a certain amount of time, and this would be an amount of time for, let's say, everybody on the net to have transmitted 2 or 3 or 4 times, they're going to assume that the token has been destroyed. So they will announce that they will create the token. But it's possible somebody else on the other side of the network is doing the same thing at the same time. So we send out a I want to be token creator message to everybody else in the net around in the circle. And we wait to see if anybody else says I want to be elected. If 2 of us want to be elected, we have a very simple way of determining who wins. Every Ethernet card has a unique number that is given to it when the card is manufactured. That's your MAC address, Media Access Control address. You could have a rule that whoever has the lowest MAC address among those who are vying to create wins. And then that person creates the token and sends it out. Now, there's elaborate ways of doing that. We don't have to get into details. There's a protocol that goes along with a lot of what we're doing here. It's called Address Resolution Protocol. Say we have the IP address of a computer, but we'd like to have the MAC address. Then we can broadcast a message to say, here's the IP address. Whoever has it, tell me what their MAC address is. We're assuming that we're looking for somebody on our own land or a neighboring land. The reason we want the MAC is because Ethernet works with the MAC, and it avoids much of the work involved with the IPv4 and IPv6 levels. It's a sort of cheaper, more local address. So the way we do it is we send out a who has, and we give an address, an IP address. And then whoever has it is supposed to respond. Now, in Wireshark, I have some Wireshark running here. You'll see that there are ops set out all the time. The problem is, I never see a reply to any of them. So I checked on why that should be happening. And the reason is the following. When somebody sends out an address resolution protocol request, it goes to everybody, so I hear it. But the reply only goes to the machine that made the request. So unless I made the request, I don't get back the reply. So most of the time you don't see the reply when you do Wireshark. There's also a reverse op, which has the MAC and you want the IP for it. If the IP is on our LAN, we broadcast to our LAN. If it's not on our LAN, we request assistance from the router that connects to other LANs. We always have to know the MAC of that router. Now, it's possible to find out what MACs you know. In the command line, you can say op-a. And this will show you for all the interfaces you have, all the different groups you belong to, we have the internet address and the physical address. These are the ones that I have there. I am 7188.147.232, I think. And you can see that I have several that come from the same group. 70.188.147. The addresses are the 6 octets. I mean, 6 groups of 2 hex digits each. Static means they could go away in a short amount of time. But I mean, static's just the opposite. It means it's set. Dynamic means it might go away. So that explains, I hope, a little bit of op. The MAC is considered a layer 2 address. That is, the layer 2 is the data link, the layer we're at right now. Layer 3 is the internet layer, network layer, and that's where the IP addresses are. So it's kind of a mess. There's IP addresses at layer 3 and MAC addresses at layer 2. Now, Ethernet chips, at the time I wrote this, which I think might have been, I don't know how many years ago, they cost as little as $20. The speed started pretty low, but now is up to the gigabits per second. And Ethernet, while it uses the star as if it were creating, if it were actually using the tokens, it doesn't. It views the LAN as if it were everybody is connected to one central node called the switch. we don't use TCP or UDP in sending to the LAN because we don't really need all the power of that. We can use the MAC addresses, and that keeps us well below layer 4. The Ethernet heading I listed here, it has a certain preamble, 7 bytes of a certain form. The reason we have this, it allows us to get in step. That is, every time there's a change from a 1 to a 0 or a 0 to a 1, then the receiver can synchronize, say, all right, that's where I need a beat, that's where I need a beat, that's where I need to read, that's where I need to read. So we send out enough of those so we and the send and the receiver are synchronized. Then we have a start frame delimiter. It says the message is now coming. Then we have the address. It is 48 bits old, but older versions were 16 bits. 48 bits versus 16 bits. 48 bits is 12 hex digits. And what did I say before? 6 groups of 2 hex digits each. There are the 64 bits. The 48 bits, the 12 hex digits. One bit of the address determines if the message is for individuals or is a multicast to everybody or to more than one. Then we have the type of the message or the length of the message. This is the only difference between the two standards, 802.3 and Internet 2. In 802.3, it's the number of bytes. If the message is not long enough, we add more bytes to pad it. The last 4 bytes represent the checksum. Now, I mentioned the RAP there, and I think I will hold off on the next portion. We'll talk about that later. So, we now have Ethernet. Ethernet is the thing we talk about. Also, you'll notice I use something called 802. When we were doing the standards in the higher layers, we talked about RFCs, requests for comments. And we'd say RFC 2214 tells us how to do such and such. Well, that's changed. The group that has controlled this side of the Internet, the bottom 3 layers sort of, is called the IEEE, the Institute of Electrical and Electronic Engineers. It's the largest professional group in the world. It's over 100,000. And it has issued many standards. The most important standard it has issued is the IEEE 802. And the way it does it is, there's an 802.1 and 802.2 and 802.3. Each one of those groups is a committee that has created a standard for something, some kind of network. 802.3 is the standard that is, for all purposes, Ethernet. 802.4 and 802.5 are standards for different kinds of LANs. One of them is a token ring. I was talking about the token that goes around. They are there, but I don't think they're really important anymore. Right now, we're up to higher numbers because people are working on WiMAX, very fast wireless. So you'll see them talking about 802.11 or 802.17. These are the frontiers, sort of the land area. They haven't yet completed all the stuff there. There are conferences. There's a conference once a year where the 802 people get together. Companies have 802 representatives. Some of you might even get involved with that in your working days. The 802 is the standard for local area networks. You can look it up. As with the RFC, it's pages upon pages upon pages upon pages of very technical information. But that's the way it has to be, because a lot of people manufacture different parts of the system, and they all have to know what they're supposed to do. So that's where we are right now. I think that'll end it for now, and we'll see you later.